I'd like to now introduce Professor Robert Hoye.
Yes, so let me take this opportunity now to introduce Professor Robert Hoye, who will give our first Wind Rising Star Award lecture this morning. Professor Robert Hoye is a lecturer on the Royal Academy of Engineering Research Fellow in the Department of Materials at Imperial College, London. Professor Hoye completed his PhD at the University of Cambridge as well as his postdoctoral stint at MIT. We are so fortunate to have Robert at this morning session, and we're looking forward to your talk. Robert, the stage is yours.
All right, thank you, Sushanta, for the very kind introduction, and I'm very honored to be one of this year's Wind Rising Star recipients. And also grateful to have the chance to share with you all the work that my team has been doing. So I'm a lecturer based at Imperial College, London, and in the Canadian system, you will call that assistant professor. So I lead a group of 10 PhD students, and we work on developing materials for clean energy conversion. So broadly speaking, our work can be categorized into three main areas. The first area is on developing defect-tolerant semiconductors, and these are materials that can achieve low non-radiative recombination rates despite high densities of defects. Essentially, this means that these materials can be efficient when made using low-temperature fabrication methods. We also work on developing scalable routes to grow new optoelectronic materials, and we specialize in vapor and solution-based methods. And we also work on developing these materials into devices. So we especially work on photovoltaics, as well as light-emitting diodes and more advanced structures such as tandem solar cells. And if you want to find out more about our work, you can follow our group website here. So in today's talk, I'll be speaking to you about our work on photovoltaics, especially on tandem solar cells, and our more recent work on indoor PV. Now, before I get started, I'd just like to thank the people who have been involved in this work. Especially, I would like to thank Rob Yacht and Tamida Huck, who are two of the PhD students I've been co-supervising, along with Judith Driscoll. I'd also like to thank my collaborators in France who specialize in the XPS measurements, as well as Professor Henry Snaith and his postdoc who I worked with to develop the lead-halide perovskite solar cells. I'd also like to thank Serena Lin and her team in the Solar Energy Research Institute of Singapore, who developed the silicon bottom cells that we use to make the tandem devices. I'd also like to thank Vincenzo Picunia and his team at Suzhou University in China. We recently collaborated together to develop the indoor photovoltaics. And I'd like to also thank the funding sources from my side. So I'd like to thank the Royal Academy of Engineering in particular. So I'd like to get started with two energy challenges. The first energy challenge is that we need to have more renewable energy, and this is one of the UN Sustainable Development Goals to provide affordable clean energy to everyone, especially in developing nations. And I'm sure we all recognize the urgency of reducing our CO2 emissions. In the UK, we have legislation that by 2050, we need to achieve net zero CO2 emissions. And this is an upgrade on our previous target, which was an 80% reduction compared to 1990 levels. Now you can see from this plot here, which is from the UK Committee on Climate Change, that to achieve this previous target, this previous 80% target, we need to almost completely decarbonize the power generation sector, as well as substantially reduce CO2 emissions from the other sectors, such as surface transport by rolling out electric vehicles, and also reducing CO2 emissions from buildings. And in this report, they outlined a further ambition scenario, which is a 96% reduction compared to 1990 levels. And to achieve this, this requires the deployment of low carbon generation sources to be increased by over a factor of 4. And of course, if we want to go beyond this and achieve net zero by 2050, we need to have more renewables available. And of course, one of the important renewable technologies are photovoltaics. Photovoltaics absorb sunlight to generate clean electricity without emitting CO2. Solar energy is a vast and abundant and reliable resource, so it's important that we can take advantage of this. So here, if this block were to represent all the energy the surface of the Earth received from the sun in 1 year, this represents how much energy the world actually needs. And there's a 3 orders of magnitude difference between the two of them. But despite this, photovoltaics only contribute to a very small fraction of all the energy generated worldwide. In the UK, for example, photovoltaics only accounts for 3% of the electricity generated. But on the other hand, it is one of the fastest growing renewable sectors. But at the same time, there's significant scope to scale up our deployment of this renewable technology and to make better use of it. The second energy challenge is the fact that in the very near future, many of the new devices that will be consuming energy will be small and wireless devices which are all connected together via the cloud. And they're part of an ecosystem called the Internet of Things ecosystem. And this will enable, for example, smart homes. So you can imagine you could be wearing some sensors on your clothing or on your watch. And when you go home, this can communicate with the sensors in your home to control some gadgets that can switch on the lights, which can adjust the heating for you, which can boil the water for you. So if they can, because they can communicate with each other, if they can enable a smart home that's responsive to the people living in there. And this can also be used to make smart healthcare systems or smart workplaces. And it's estimated that by 2025, we will have 75 billion devices part of this Internet of Things ecosystem or IoT ecosystem. And many of these devices will be small devices, wireless devices, which are located in hard to reach areas. For example, you may have some sensors located on trees or outside of buildings to detect the wind velocity, for example. So you can't connect this simply to the grid. You need to have portable power supplies. And maybe the first thing you think about would be to use batteries for all these devices. And using batteries works if you have millions of devices. But as soon as you go towards the trillion device level, as soon as you go beyond a certain number of devices and a certain level of complexity, it no longer becomes practical to use batteries to power every single one of these wireless devices. And some people predict that if we solely rely on batteries, we would prevent 80% of the potential of IoT from being realized. So we need to have alternative ways to power these portable devices. And bear in mind that many of these devices will be located indoors. So one option will be to use indoor solar cells. And these solar cells could last for the entire lifetime of the electronic gadget itself. You can use them in conjunction with batteries. So you can use the solar cells to charge up the batteries. You can use the batteries when the lights are off, or you can just use the solar cells by themselves. And indoor photovoltaics have been rapidly growing. So for those of you who have used a calculator with a built-in solar cell, you've already used an indoor solar cell. And that's probably made from hydrogen perturbated amorphous silicon, which is the most common material used for indoor PV. This material is about 10% efficient or less than that, but still it's enough to power some of these smaller gadgets which don't require that much power. Of course, if you want to power the larger gadgets like the Wi-Fi sources, then you need to have more efficient materials for indoor PV. But nevertheless, the indoor photovoltaics market has been rapidly growing, and the growth rate is even higher than for outdoor PV, and also faster than the wireless sensors market. But it would be better if we could find materials that could be more efficient in the future. So I've talked about 2 energy challenges, and I said that for both of them, we could address these challenges using solar cells. So what are solar cells, and how do they produce electricity? So on the left-hand side here, you can see the structure for a typical photovoltaic device. And in this photovoltaic device, the key component is a light absorber here. This is a semiconductor which absorbs sunlight or indoor light, and we have to have 2 other semiconductors to only extract one of the carriers, either the electrons or the holes. And we have 2 electrodes on either side. And one of these electrodes needs to be transparent so that we can shine light through into the device and get so the light reaches the absorber layer itself. Now over here you can see the band structure for this photovoltaic device stack, and we would shine light in through the transparent electrode that gets absorbed. We excite an electron across the band gap, and because we have this built-in electric field, we can separate the electrons and holes in opposite directions and extract that to generate electricity. So solar cells involve no mechanically moving parts, and there's no CO2 emitted during this process. So here you see a chart from the US National Renewable Energy Lab that summarizes some of the key photovoltaic technologies. And for the outdoor market, by far the most common material used is crystalline silicon, which is represented by these blue squares here. And you can see that this technology has been developed for well over 4 decades and is now very mature. The efficiencies in the lab have reached 27%, which is very close to the efficiency limit of 29%. There's also a lot of other newer technologies, which are given in this bottom right-hand corner here. So let's zoom in into these. And you can see that one of the fastest growing new technologies is represented by these yellow circles here. And these are the lead-halide perovskite solar cells. These are based on polycrystalline thin films. And even though they've been developed for just 1 decade, these are already more efficient than multicrystalline silicon solar cells. And they're in fact almost as efficient as the best single crystalline silicon devices. So that's quite remarkable. You can also have these perovskites work in tandem, in conjunction with silicon solar cells. And these tandem devices are represented by these blue triangles here. So this first point was the first certified efficiency. So the first tandem device that was certified by the National Renewable Energy Lab. And this project was led by Stanford and Arizona State University. And previously, when I was a postdoc at MIT, I contributed was developing the recombination contacts that went into this tandem device. And you can see that after only a few years of development, the efficiencies have skyrocketed. The certified highest efficiency is now at 29.1%. And this is larger than the best efficiency for single-junction silicon. It's also larger than the efficiency limit for silicon working by itself. So this is very promising, and people predict that it's realistic and practical to commercialize these perovskite silicon tandems and make large-scale modules that have 35% efficiency in the very near future. So what are these perovskites? Well, when I say perovskites, I'm actually referring to a family of materials which share the same crystal structure. And these materials, the structure is shown here, and these materials have 3 different components. They have a A-site cation, a monovalent cation, they have a B-site cation, and they have an anion. In this case here, our B-site cation is lead, and each lead cation is coordinated with 6 halides. This could be iodide, for example. And these lead halide octahedra share corners to form this cubic unit cell. And to hold the whole thing together, we have this monovalent A-site cation, which is the right size to fit exactly within this void. And typically, this will be an organic cation, such as methylammonium. And what's rather unusual about the perovskites is that they can be made at low temperature using solution processing methods. So you spin coat these films, you anneal at just 100 degrees Celsius, and you can make solar cells that are almost as efficient as the best single crystalline silicon solar cells. Now, if you contrast that to silicon, to make the best silicon devices, you have to process at above 1400 degrees Celsius to melt the silicon and draw out single crystalline silicon that you slice up, and then you have to process in a very clean environment. By contrast with the perovskites, you can process them inside a normal lab-based glove box or inside a normal dry lab, and just anneal at 100 degrees Celsius to get these high efficiencies. So the CO2 footprint of manufacturing perovskites is also a lot lower than that for making crystalline silicon devices. So in today's talk, I want to cover our work which addresses 2 challenges. The first challenge is how can we use perovskite solar cells to lower the cost to power produce ratio of photovoltaics. And I mentioned earlier that For outdoor PV, the most common material used is crystalline silicon. And that represents 94.5% of the world's photovoltaics market. And after so many years of development, the cost of manufacturing silicon has come down a lot. So the silicon module itself only accounts for about 30% of the total cost of solar. So if you make a fractional improvement in efficiency or fractional reduction in the cost, it's not going to have a big impact on this total cost to power ratio for solar cells. So what we can do to substantially push down this ratio is we could put it in combination with a perovskite to make what I would call a tandem device. I'll explain a bit later what that is. And this can break the efficiency limit, so we could increase the efficiencies, increase the power produced. And if we can do that without significantly adding to the cost, we can push down this ratio. And the second challenge is to do with the fact that lead is toxic, it's bioaccumulative, and in these perovskites, the lead is easily accessible. So this is a water-soluble material. If you were to drop it into a lake, for example, it would dissolve and it could contaminate the water supply with lead. So this poses a risk to the end user. And I should emphasize that people are working on this. People are developing sequestration methods and ways to safely recycle the lead. But at the same time, it's also important to think about how we could find alternative materials which could have the same properties, but which are also safe and stable materials as well. So in this talk, I have 3 sections. The first 2 sections address the first challenge, and the third section addresses the second challenge. So let's get started with the first section. This is on tandem solar cells. In particular, I want to talk about the buffer layer. So a tandem solar cell is a bit like a tandem bicycle. In a tandem bicycle, you have 2 people working together to produce more power. In a tandem solar cell, you have 2 solar cells working together to convert a larger fraction of the solar spectrum into electrical energy. And for this to work, the 2 solar cells have to be complementary. So perovskites and silicon are complementary. Silicon absorbs near-infrared light. The perovskites absorb visible light. And this working together, they can achieve higher efficiencies than the maximum that each alone could achieve. And there's 2 ways of doing this. Two common ways of doing this. You can either make 2 separate solar cells and measure them separately or connect them separately. And this is called a 4-terminal tandem. Or you can integrate the 2 together to make just one device. And this monolithic tandem is called a 2-terminal tandem. Now, in both cases, the transparent electrode, the top electrode has to be transparent so that we can emit light to both the top and bottom cells. And usually this electrode would be transparent conducting oxide, for example, could be indium tin oxide. And this would usually be grown by sputter deposition. Now, sputter deposition is a very high energy process. So when you are sputtering something, you have very high energy atoms which are colliding with your substrate, in this case, it's the perovskite device. And because the perovskites and the organic charge transport layer are quite soft materials, you can easily damage these 2 layers. So we have to have an oxide layer that can protect, which is a buffer layer which protects the perovskite top cell. And this oxide layer doesn't need to be very thick. 10 nanometers has been found to be sufficient. And currently, the methods for growing this oxide layer include spin coating, some oxide nanoparticles. They include atomic layer deposition. You can also thermally evaporate some oxides, and some people do use sputter deposition, but this is not very commonly used because, as I mentioned, sputter deposition is a very high energy process. Now, with these oxides, the role is not just to mechanically protect the perovskite device. The oxides also are electronically integrated with the device, and they have to transport the photo-generated carriers. So the electronic properties are also important. And for those of you who have worked with oxides, you would know that, as a rule of thumb, the higher in temperature you can process the oxides, the better the electronic properties. And now that works if you're growing onto glass. If you're growing onto a perovskite solar cell, then you're much more limited in what temperatures you could use, because the perovskite is not thermally stable. And so far, the maximum temperature people have been able to use is 110 degrees Celsius, which at the same time significantly restricts what mobilities you can achieve with the oxide buffer layer. So that's the main problem. But some of the other requirements for the oxide buffer layer include the fact that it has to be pinhole free, it has to be the growth method needs to be fast and scalable, so you can use this on an industrial scale, and so that you make sure the top cell doesn't add too much to the costs of the bottom cell when you're making a tandem. And also the oxide needs to be conformal, because the most efficient perovskite silicon tandems are based off front texture silicon, and it's front textured to make sure you have minimal light reflection, so you get better light management. So you need to make sure that the oxide is also conformal to these micron-sized pyramids in your solar cell. And here you can see what happens if you were to use atomic layer deposition to grow TiO2 or aluminium doped zinc oxide directly onto methammonium-lead-halide perovskites. You can see that it turns yellow because the perovskites degraded when you're processing these oxides at only 100 degrees Celsius. And that's partly because the deposition time takes 1 hour in ALD. But at the same time, you can see that the higher in temperature you can process the oxides, the better the mobility is. So there's these two competing factors here. So what I wanted to do was to investigate an alternative method to the existing methods for growing the oxide buffer layers. And this method I call atmospheric pressure chemical vapor deposition. And you may have heard about this reactor from Professor Kevin Mossman, who was part of WIN. And Kevin was my mentor when I did my PhD in Cambridge and when I was working on this reactor. So in this reactor, we have some liquid precursors, and these are the same. These can be the same precursors as an atomic layer deposition. You bubble through them using an inert gas, which carries them to this gas manifold here. So here's a 3D sketch of the gas manifold, and the precursors are introduced from both the right-hand side and the left-hand side, and there's a header channel running through it, which guides the gases to go vertically down to the substrate, and you move the substrate backwards and forwards to grow the oxides layer by layer. Now, if you have a very small spacing between the bottom of the manifold and the top of the substrate, then you can ensure that each of these different gas channels is spatially separated from each other. And here you have the metal precursor gas channel. These blue channels are the oxidant channels, and these are separated with these inert gas channels. So if you ensure there's spatial separation, then you can achieve ALD much faster and in open air. So you have heard about this from Professor Musselman. This is spatial ALD. What I tend to do is I tend to have a large spacing between the bottom of the manifold and the substrate, so that there's mixing of these precursors in the gas phase. So we get CVD rather than ALD growth. And what I found is that this gives very similar properties to ALD films. So the oxides are pinhole free, they're uniform over the deposition area, and also they're conformal onto high aspect ratio nanostructures. So I get the benefits of ALD, but I also get the benefit of the fact that with CVD, I get a much higher growth rate. And you see that here, this is for the example of zinc oxide with conventional temporal ALD. So that's your standard ALD reactor where you put precursor 1 in step 1, then you purge, then put in precursor 2 in step 3, where you separate the two precursors in space in different pulses. Then you have a very low growth rate between 0.1 and 0.2 nanometers per second, whereas by APCVD, the growth rate is an order of magnitude larger. So what that means is that instead of taking 1 hour to grow 10 nanometers of your oxide, you can complete the deposition within a couple of minutes in open air. And our question is, so we would use this to grow the oxide buffer layer onto the perovskite device, which is held by this oscillating substrate. Our question is, can we take advantage of this to significantly reduce the exposure time of the perovskite solar cell to the processing temperature? And can we use this to allow us to use a wider range of deposition temperatures without degrading the perovskite? And does this in turn lead to improved efficiencies if we can use higher processing temperatures? So I first of all investigated the use of N-type oxides, and these were grown onto a PIN-structured perovskite solar cell. And what PIN means is that I'm using a whole transport layer on the bottom. I'm using electron transfer layer on top, which is PCBM. And I'm growing these N-type. I need to use N-type oxide to grow an oxide buffer layer over this. So here I'm comparing 3 different N-type oxides, 3 different options. And these are titanium oxide, tin oxide, and zinc oxide. And for the perovskite, I'm comparing two different perovskites. So the first is methylammonium lead iodide. Now, this is not very commonly used anymore, and the reason why we investigated this is for exactly the same reason, because it's very thermally sensitive. It's the most thermally sensitive perovskite. This would give us the worst case scenario. And I wanted to compare that against more state-of-the-art perovskites, which are these triple cation perovskites, where I'm mixing cesium, methylammonium, and formamidinium in the A site of the perovskite structure. And here is the setup for my APCVD reactor. And here you can see the metal precursors. So that's in this red channel here for the three different oxides. And I'm mainly comparing two different growth conditions. I'm comparing what I call mild conditions, which is where I'm using oxygen gas as the oxidant. And this is less reactive to the perovskite. I just want to emphasize that with ALD, I can't use oxygen gas. It's not reactive enough, but with CVD, I can. So this is something different with APCVD compared to ALD. And this oxidant is less reactive with the perovskite. I'm using a low deposition temperature of 100 degrees Celsius, which is within the range of temperatures that people have used with oxide buffer layers in the past. And I'm comparing this against strong conditions, where I'm using water vapor, which is much more reactive with the perovskite, and a much higher deposition temperature, which is higher than the range of temperatures people have used in the past for the oxide buffer layer. So first of all, this is what happens when we brew APCVD TiO2 over methylammonium lead iodide. And we're taking the worst case scenario. We're using the strong deposition conditions with the most thermally sensitive perovskite. And you can see that it stays the same. And this contrasts to what I showed you earlier, where people use ALD to grow TiO2 at only 100 degrees Celsius. And after the 1 hour it took to grow 10 nanometers, the perovskite completely degraded. But with this technique, we're growing 7 nanometers. And because the growth rate is several orders of magnitude higher than for ALD, we can keep the deposition time within a minute. And this, you can see, avoids visually changing the appearance of the perovskite, and as well as avoiding any change to the morphology as well. And here you can see the bulk properties of the perovskite stack. So this shows you the diffraction pattern for this bilayer of methylammonium lead iodide with TiO2 growing on top under strong conditions. And if there were any lead iodide degradation product, it would appear here. And I emphasize this is on a logarithmic scale, which would accentuate any low intensity diffraction peaks. But you can see there's no peak that appeared. So we avoid any bulk degradation to the perovskite. And we also look at the time resolved PL, and we found that after the growth of the TiO2, we have also avoid decreasing the time, the PL lifetime, which shows us that we're not introducing any extra non-radiative recombination channels. So now we want to see, so we know the bulk remains the same, but what happens at the surface? So we looked at the buried perovskite interface using XPS. So the nitrogen core peak comes from the methylammonium, the lead and the iodide comes from the inorganic sublattice of the perovskite. And you can see that after growing the TiO2 under mild conditions, we do see this small peak appearing here around 400 electron volts core level binding energy. And this is from degradation products. So there is some degradation of the methylammonium. And you can see that the lead peak and the iodine peak becomes slightly wider. So there's degradation of the organic component and the inorganic sublattice. At the same time, the amount of degradation is very small. It's much less than what you would get if you were to use alternative techniques at the same temperatures where even the bulk would degrade. So this is quite promising. And we next wanted to see what happens if we have a very thin layer of our electron transport layer, because in our full devices, we need to use PCBM, 40 nanometers of PCBM to form a good interface for electron extraction from the perovskite. Now, of course, with XPS, we can't see through 40 nanometers of PCBM, and we can't really mill through it either. It's not really amenable to milling. So to look at the buried perovskite interface, we thinned down the PCBM layer by decreasing its concentration when we solution processed it. And that meant that this is a nominal thickness, but we had some regions as well where the thickness was much less than this, and therefore the total thickness of the overlayers was small enough that we could see through them with the XPS and look at the buried perovskite interface. And what we can see here is that we avoid changing the nitrogen, lead, and iodine core level peaks. So we can avoid any degradation to the perovskite, even if we have a very thin layer of PCBM. And this is TiO2 grown under strong conditions. And this is just to show you the morphology of the perovskite before and after depositing this thin layer of PCBM, to show you that we have some regions of the PCBM where it's only 1 or 2 monolayers thick, and you can see the morphology of the underlying perovskite through it. And these are the layers which are thin enough for us to see through with XPS. So now that we know that we could avoid degrading both the bulk and the surface when we're growing TiO2, 7 nanometers of TiO2 by APCVD, even under strong conditions, we now want to see what the impact is on the device performance. So we looked at both the methammonium lead iodide and the triple cation perovskite devices, and the black diamonds represent the control efficiencies, which is where we don't have any oxide between the PCBM and the top electrodes. And what you can see, so the red diamonds represents devices with TiO2 growing under mild conditions, and the blue diamonds represents devices with TiO2 growing under strong conditions. And you can see that with these oxide overlayers, not only are we avoiding decreasing the efficiency, we actually achieve improvement in the efficiency. And the reason for that is because the spin-coated PCBM layer has pinholes in it, which lead to shunting, a little bit of shunting, whereas the ALD TiO2, even if it's, APCVD TiO2, even if it's only 7 nanometers thick, is still dense and pinhole-free and can block these shunt pathways. So we can improve the fill factors and achieve these improvements in the efficiency. And now we fixed the oxidant to water vapor, and we varied the deposition temperature over a wide range up to 220 degrees Celsius. And when we looked at the XRD patterns, we found that there was no bulk degradation even at this high temperature, because the deposition time was so short. And we can see that in the devices, the efficiencies go up to we can go up to 180 degrees Celsius in the deposition temperature before we start having device efficiencies that go below that of the control. And the question is, why is there improvement in the efficiency as we increase the deposition temperature for the oxide? And we measured the resistivity oxide, and as we expected, as we grew at higher temperatures, the resistivity became lower. So the oxide buffer layer makes a smaller contribution to the total series resistance of the device itself. So now that we have some very promising results with TiO2, we wanted to see whether ABCVD could be more broadly applicable. And so here we're looking at tin oxide and also zinc oxide, which are both N-type oxides. And here we grow the oxides directly onto the perovskites, so both methammonium lead iodide and triple cation perovskite thin films. And we looked at the diffraction patterns, and we saw that when we grew the zinc oxide, there was the appearance of extra lead iodide. And this is consistent with the literature, which suggests that zinc oxide could interact with the perovskite to deprotonate and cause degradation. There's also literature that suggests that the dialpha zinc metal precursor for the zinc oxide can degrade the perovskite itself. So this is consistent with the literature. When we look at the tin oxide, by contrast, there was no extra lead iodide peak. With the triple cation perovskites, the as-grown thin films have residual lead iodide. After growing tin oxide directly over it, after about 2 minutes of deposition, there was no increase in the lead iodide diffraction peak, which showing that there's no degradation of this triple cation perovskite. And consistent with these diffraction results, we found that the efficiencies went down when we were using zinc oxide, but they didn't significantly decrease when we used tin oxide instead. And in fact, when we used a buffer layer of tin oxide grown under mild conditions, we saw an improvement in the efficiency compared to the control, at least for the triple cation devices. And we optimized the thickness of the tin oxide buffer layer with the triple cation devices, and here we used more reflective aluminium top electrodes, and we were able to improve the efficiency from 16.5% to 19.4%, and the improvements came about through this increase in the fill factor up to a value of 84%. So this is quite a good improvement, and the reason for that is again because the PCBM layer has some pinholes, which leads to a low shunt resistance, and when we grow the dense tin oxide layer over it, we block these shunt pathways and we reduce the reverse bias current density. But thus leading to improving the fill factor by increasing the shunt resistance. And very quickly, I just want to mention that we grew some textured perovskites, and we found that the tin oxide was conformal to that, which is important if we want to make a textured perovskite silicon tandem. So just to summarize the first part, we introduced this alternative technique, APCVD, and we found that it fulfills all the requirements for the oxide buffer layer. In particular, we can widen the processing window because the exposure time of the perovskite to the reaction temperature is much lower than for any of these other deposition methods for the oxide buffer layer. So now I want to move on to the second section, and we're staying with tandem solar cells, or the idea of making tandem solar cells, and also staying with the theme of making the buffer layer. But this time, I want to talk about the application of APCVD for growing P-type oxides. So why is that important? Well, if we want to make an NIP-structured perovskite top cell, we have to have a P-type oxide between the whole transport layer and the top electrodes. And why is NIP important? Well, if we look at the history of the development for perovskite solar cells, every single year, the highest certified efficiency came from a perovskite made in the NIP structure. So currently, people use high work function N-type oxides as a buffer layer. In particular, people use molybdenum oxide, which is grown by thermal evaporation. But a problem with this is that it reacts with the perovskite and it causes degradation. So even if you encapsulate your perovskite device, you can't guarantee that eventually you won't have some molybdenum oxide reacting with the perovskite through the organic charge transport layer and causing accelerated degradation. So we want to look at alternatives, so why not look at a stable P-type oxide as an alternative to these high work function N-type oxides. And when we did this work, people hadn't looked into these P-type oxides buffer layers before, so we looked towards what oxides were used as whole transport layers beneath PIN structured perovskites. And the two most common whole transport layers used are nickel oxide and Cu2O. And of these two, we picked Cu2O because this can be grown at relatively low temperatures. So there's a previous work by David Muñoz-Rojas, who previously also worked in Cambridge, who now has his own group in France. And he showed that we can grow Cu2O using APSALD at temperatures of only 125 degrees Celsius. By contrast, we found that we need to use deposition temperatures of 300 degrees Celsius or higher to grow the nickel oxide. And that, of course, is too high to grow oxides onto perovskites. Okay, I'll just move more quickly. So this is the setup for our APCVD reactor for growing the P-type oxides. We use Cupra Select as our metal precursor. And here you can see a photograph of the films, and you can see it was uniform over the 6 centimeter squared deposition area, and the variation in film thickness was only 5% of the mean. One of the problems with Cu2O is that it has a narrow band gap, so it absorbs visible light. So if we have it too thick, it's going to absorb some of the light that would otherwise go to the perovskite. So we made cuprous oxide films which are only 3 nanometers thick, and we found that it was pinhole free, and because it's so thin, the transmittance was very high. It was close to 100% over the visible wavelength range. We also showed that the cuprous oxide growing was phase pure, Cu2O, with a copper in the 1+ oxidation state. And we found that we can grow at 100 degrees Celsius, and this avoided any degradation to the perovskite. The total deposition time was about 2 minutes. And we could also can avoid introducing any non-radiative recombination channels to the perovskite. So here you can see the device structure and the device stack. So this is the cross-sectional SCM image of our semi-transparent devices, where we have FTO as our substrate. This is a transparent bottom electrode, and we sputter ITO as our transparent top electrode. we have PTA as our whole transport layer, and between the PTA and the ITA, we have our 3 nanometers of cuprous oxide. And one of the questions, of course, is if it's only 3 nanometers thick, is that enough to protect the perovskite from sputter damage? And the answer is yes, it is. So this red curve is the IV curve for our perovskite devices with ITO sputtered without any cuprous oxide, and the blue curve is with cuprous oxide. And you can see that having a cuprous oxide buffer layer is sufficient for protecting the perovskite from sputter damage and allowing us to have a good fill factor with a decent efficiency of 16.7% for semi-transparent devices, and that's comparable to the state-of-the-art for semi-transparent perovskite top cells. So we work with our collaborators in Singapore, and we use these as top cells in 4-terminal tandems with silicon, and we achieve tandem efficiencies that reach up to 24.4%. So this is just to summarize part 2, and because I'm running short on time, I just want to move on to the third section now. And this is about the second challenge, which is, can we find lead-free alternatives to the perovskites? So the unique feature about the perovskites is that you can process them at relatively low temperatures using very simple fabrication methods. They have lots of defects, but they still can achieve high efficiencies. And we call this property defect tolerance. And what we know from Shockley-Reed-Hall statistics is that the rate of non-radiative recombination depends not just on how many defects you have, but also where the defects are within the band gap. So this is a model for defect tolerance based off the electronic structure. So on the left-hand side, we have the structure for a traditional semiconductor like silicon or gallium arsenide. And in these materials, the atomic orbitals hybridize to form a bonding and anti-bonding orbital pair across the band gap. You then end up with the original atomic orbitals being close to the middle of the band gap. So when you break bonds and have defects, the defect states will form at energies close to the middle of the band gap. And this is very harmful, causes high rates of non-radiative recombination. By contrast, the perovskites have a very different electronic structure, which results in the atomic orbitals being close to the bands rather than in the middle of the band gap. So when you form defect states, the defect states will form resonant within the bands, or if they do form within the band gap, they'll be shallow within the band gap, meaning they're close to one of the band edges, which is much less harmful, gives much lower rates of non-radiative recombination. So we hypothesized that we could find materials with this defect tolerance if we could find materials with a very similar electronic structure. And we looked towards materials with partially oxide p-block cations, such as bismuth. So bismuth forms a stable 3+ oxidation state, which means that it then has the same electron configuration as lead does. And one of the materials we looked at is bismuth oxyiodide. Now, this is not a material you have thought about if you were just looking for a lead-free perovskite. It doesn't have a perovskite crystal structure. It doesn't have a chemical, it's not chemically analogous to the perovskite either. But the reason why we want to look at it is because we believe that this material could replicate the features of the perovskites to replicate its defect tolerance. And what's also good about bismuth is that it's green, it's non-toxic. So right next to bismuth, you have lead and then thallium, and then mercury, so all the toxic elements. And on the other side, you have polonium and acetine, so the radioactive elements. But bismuth is neither toxic nor radioactive, so it's in a sweet spot in poisonous corridor on the periodic table. So you use bismuth-based compounds, for example, in over-the-counter stomach medicine. And also the abundance of bismuth in the earth that's known is sufficient for commercialization as well. So we grew bismuth oxyiodide by CVD using this tube furnace, and it has a band gap of 1.9 electron volts, so that results in this red appearance that you see here. And we left these films in ambient air for 197 days, and we found that it stayed the same. So it was stable over this testing period. Now contrast that to the perovskites. If I were to leave methammonium lead iodide in air in the same conditions, it would degrade within 5 days. This material is at least 2 orders of magnitude more air stable than the perovskites are. We next looked at the defect tolerance, and these calculations were done by one of the PhD students I worked with at MIT, so that was Rachel Kirchen, who also worked with Mladen Stevanovic, based at the National Renewable Energy Lab. And what they calculated was the defect formation energy, and that's because the concentration of a defect has an Arrhenius relationship to the defect formation energy. If this formation energy is larger, the concentration of the defect is smaller. And in this diagram, 0 eV Fermi energy represents the valence band maximum, this represents the conduction band minimum, and this white space represents the band gap. And these different lines here represent different defects. For example, this dashed line is a bismuth vacancy. And as a rule of thumb, if the formation energy is above 1.5 electron volts, then the concentration of the defect is so low that you may as well neglect it. So we only are looking at a small handful of these defects here, the bismuth vacancy, the iodine vacancy, and these two anti-sites here. And the slope of these lines represents the charge state of the defect. We're looking for the Fermi energy in which there's a change in the slope. These are called transition levels, and that's where the defect state can trap an electron or hole to change its charge state. So you can think of these as where the traps are within the band gap. And what you can see here is that for these lowest formation energy defects, they don't have these traps within the band gap. Or if they do, they're shallow. And this agrees with our hypothesis that the defects will be either resonant within the bands or shallow within the band gap. And this shows that this material tolerates these vacancy and anti-site defects that we considered. So we next made these into devices, and one of the challenges is that the bismuth oxide is very heavily textured. So we can't just spin coat the zinc oxide electron transport layer on top. But what I can use is I can use the APCVD reactor I was talking about earlier to grow the zinc oxide conformally onto the textured bismuth oxide. Now, I mentioned earlier that bismuth oxide has a band gap of 1.9 electron volts. And you can see the external quantum efficiency spectrum, which shows you the fraction of light at different wavelengths, which are converted to electrons that are collected. And that's given by this green line here for bismuth oxide. And you can see that this yellow region here, that's the solar spectrum, and there's lots of infrared light. I'll quickly wrap up. So there's lots of light which won't get absorbed. So under one sun illumination, they're not very efficient, but under indoor lighting, so fluorescent lighting or white light LED lighting, where the spectrum is much better matched with the EQ spectrum for bismuth oxide, the efficiencies are much higher and they reach 4.4%. And that's significant because currently the industry standard for indoor PV is amorphous silicon, which has efficiencies between 4.4% and 9.2%. So with this first demonstration, we can already achieve efficiencies within the range of efficiencies for the commercial technology. And we demonstrated that these bismuth oxide devices were sufficient for powering NOT gates. And here you can see the characteristics here. So with a high voltage input, we get a low output. For low input, we get a high output. So that's exactly how a NOT gate should work. And these devices were already adequate for powering small electronic devices. And we wanted to see what the future potential is for this material. And we calculated that if all the indoor light was absorbed by the bismuth oxide and converted to charge, we would have an efficiency that would reach 44%. We also looked at a wide range of other perovskite-inspired materials, and we showed that these materials, because they have band gaps close to the optimum for indoor PV, we could reach efficiencies within the 40 to 60% range in the future. And the final point I want to make is that we want to look at what we need to do to go from where we are right now for bismuth oxide to where the future potential is. And one of the things that we need to do is to have new hole transport layers with a higher work function, so we don't have downwards band bending at the interface between bismuth oxide and nickel oxide. So I just want to very quickly wrap up. So the first part was about, we demonstrated APCVD as a very promising and effective method for growing oxide buffer layers on thermally sensitive perovskite devices. We demonstrated that with N-type oxides and also with P-type oxides. So here you see a photograph of the 4-terminal tandems. And finally, we looked at lead-free alternatives to the perovskites. And one of those materials is bismuth oxide, which we showed to be very promising for indoor PV. And before I just finish, I just wanted to say that I have 2 vacancies in my group, a postdoc vacancy and a PhD vacancy, and these are open to people of any nationality. So thank you very much for listening, and I'd be very happy to answer questions.